Welcome to this video course on optimization methods. This course is a 15-hour introductory course. It is part of the teaching unit Advanced Control 2, together with the teaching activity Model Predictive Control, given by my colleague Thomas Museur, and the teaching activity Advanced Control on Embedded Systems, which is a project-based learning laboratory. This is the outline of the course. The first section is the introduction. It gives you the practicalities of the course and the main references that have been used when compiling this course. The second section is an introduction to optimization. It is also a reminder of unconstrained optimization, and it presents the main classes of optimization problems that you're likely to encounter in practice. The third section is about one such class of optimization problems, the linear program. This is the optimization of a linear objective function subject to linear equality and inequality constraints. The fourth section derives the algorithm that is used to solve linear programs, and this leads to the simplex method. Section 5 considers nonlinear objective functions with nonlinear equality and inequality constraints. We will focus on constrained optimization problems with equality constraints, and this leads to the Lagrange multiplier method with an analytic solution, and this method is used in the teaching unit Model Predictive Control. Constrained optimization problems with inequality constraints and the associated so-called Karum-Kush-Tucker or KKT conditions are not part of this course. The slides are there for your information. Section 6 gives an introduction on numerical or iterative optimization for unconstrained problems. This section will be used in the teaching unit System Identification. The exam is a closed book examination with exercises and theoretical questions. The theoretical questions will mainly focus on the last section on numerical optimization. In the exercises, you will have to deal with unconstrained optimization problems and convexity, two-phase simplex method problems, and finally Lagrange multiplier method problems. Notice that you will most probably receive an optimization problem in words. You have then to be capable to convert the word problem into a mathematical optimization problem by setting up the objective function and the constraints. If you see typos, mistakes, or if you have ideas on how to improve the course, do not hesitate to contact me, preferably by email. I will really welcome this. MATLAB is an important tool for optimization. Do not hesitate to try some of the sample code available in the course. It will speed up the learning process. Note that the MATLAB optimization toolbox is part of the Student Suite license. If you plan to buy this license, do not forget to add the System Identification Toolbox license if you are a student in control engineering. These are the references that have been used to construct this course. I draw your attention on the following reference. The copyright of this book, Convex Optimization, is held by Cambridge University Press, but they make the book available on the web. You can use this clickable link to access the PDF version of the book. This reference will also help you if you want to take the study of optimization further. Let us start this introduction to optimization with a definition of optimization. If you look in a dictionary, you will find something like optimization is the search for the best element according to some criterion in a set of available alternatives. In mathematical terms, we speak of the minimization or maximization of the objective function f of x that depends on the variable vector x subject to constraints. So here f of x takes inputs x that are in Rn and it produces a scalar output, right? Well, very often x is constrained to live in a subset of Rn. So we'll have x is in a feasible region S that is included in Rn. Right? So x is a vector here, and you can see this from the notation. When you have a lowercase letter x in bold, it denotes a vector. Here you have a lowercase letter x that is not in bold, so this denotes a scalar. F of x depends only on one scalar variable. So we can write, for instance, the maximization problem as follows. So we have the maximum of f of x, where x is constrained to live in a feasible set S that is included in Rn. As you can see, there is an equivalence between minimization and maximization problems. The x that minimizes f of x is also the x that maximizes minus f of x. So we can write that this problem is equivalent to the following problem. So minus the minimum of minus f of x, where x is constrained to live in the same feasible region S that is included in Rn. And we'll use this extensively in the section on linear programming, where we will only consider minimization problems. And if you are given a maximization problem, well, then you have to transform it into a minimization problem. Here we consider an optimization problem with an objective function f of x, where x is in Rn. So there are n independent variables, and in this particular case here, n is equal to 2, so x is in R square, n is equal to 2, so there are two independent variables, x1 and x2, and what you see over here are the level curves of f of x. So it's the locus of all points where f of x has the same value k, where k is some scalar. So for instance, this is the locus of all points with f of x is equal to k1. This is the locus of all points where f of x is k2, and k2 is smaller than k1. And as you can see over here, this is the unconstrained minimum. In many problems there are equality constraints, and in this course the equality constraint will take the form g of x is equal to 0. In general, if x is in Rn, g of x is equal to 0 will produce an hypersurface of dimension n minus 1. Here we're working in R square, so n is equal to 2, so g of x will produce a curved line. So for this constraint equality problem, we have now that we are looking for the minimum of f of x, where x is in the feasible region S, included in this case in R square, and the feasible region S is the set of all x such that g of x is equal to 0, right? And well, this feasible set is given here in blue, and when we look for all solutions of g of x is equal to 0, and we look for the solution with the smallest cost f of x, we see that it corresponds to this point here in blue, and we see that the constraint minimum with this equality constraint is different, of course, to the unconstrained solution. In some cases there are inequality constraints, and in this course the inequality constraints will take the form h of x is smaller or equal to 0, and this defines a feasible region S, that is, well, the set of all x such that h of x is smaller or equal to 0. Okay, and this constraint optimization problem with inequality constraints takes the form minimum of f of x, where x is in S, a subset in this case of R square. And of course, the solution of this constraint minimization problem with inequality constraints, and here it's this dot over here, this point here in magenta, is different to the solution of the unconstrained problem given here in green. In some cases you have both equality constraints of the type g of x is equal to 0 and inequality constraints of the type h of x smaller or equal to 0. In this case, for instance, we have one equality constraint and one inequality constraint. This yields a new feasible region. It's the part of j of x is equal to 0 that lies inside the region h of x smaller or equal to 0. And of course, if you take all the x's that are in the feasible region, the one that is going to give you the smallest cost f of x is now shown here in red. And as you can see, again we have yet another solution to the constraint optimization problem, and again it is different to the unconstrained solution. Note that in this case the feasible region S is the set of all x such that g of x is equal to 0 and h of x is smaller or equal to 0. Sometimes a function has a number of local minima, one of them being the global minimum. Sometimes algorithms, like the ones that are presented in the last section on numerical optimization, end up in a local minimum. They get stuck in this local minimum. Some of these algorithms are based on gradient descent. So they will start from a given starting point, right? Let's say this point over here. And at this point, the gradient will be evaluated. Let's say that it is shown over here. And then the method will go into the inverse gradient direction because it looks for the minimum, and it will do this by advancing step by step, each time recomputing the gradient and going into the inverse gradient direction until this method finds a local minimum that is not necessarily the global minimum. To understand this, use the following analogy and look for the way a water droplet flows from high altitudes. Depending where this droplet is falling, it might or not end up in a global minimum. Okay, so if this droplet falls over here, it will end up in a local minimum. If this droplet falls over here, then it will end up in the global minimum. The message is then that for those kind of algorithms, it is necessary to redo the optimization several times with different starting points. First and second order partial derivatives of the objective function, but also of the constraints, play an important role in optimization. In the gradient vector, which is a column vector, the first order partial derivatives are stacked one above the other. It is the generalization of the derivative of a function of one variable. The Hessian matrix is a symmetric square matrix where the second order partial derivatives of f of x are stacked as shown on the screen. It is the generalization of the second derivative for a function of one variable. A prerequisite for this course is that you know the basics of derivatives calculus. This means that you know the derivatives of the commonly used functions, that you can use the derivative chain rule, and that you can compute a partial derivative. In this slide you can see the second order sufficient conditions for a strict local minimum. You have seen these conditions previously in a slightly different format, but here we will use the concept of positive definiteness. We have seen in the course Linear Algebra and Applications, part of the teaching unit Advanced Control 1, that a positive definite matrix is a matrix for which this quantity x transpose ax is positive for any non-zero vector x, right? And there were several ways to establish if a matrix is positive definite or not. You can work with the pivots, compute the pivots. If they are all positive, the matrix is positive definite. You can work with the eigenvalues. This is probably a little bit more complicated. If they are all positive, then the matrix is positive definite. Or you can also compute the upper left determinants. If they're all positive, well, the matrix is positive definite. If this comes as a surprise, well, you should go back to this course of linear algebra. Let us consider a function f of x that is scalar valued and that takes as input a vector x that is in Rn, and assume that this function has a continuous gradient and Hessian on a feasible region S, and consider a point x star that lies inside the region S, so not on the borders. Let us now assume that the gradient of f is the zero vector in x star and that the Hessian of f is positive definite in x star. Then x star is a strict relative local minimum of the objective function f of x. And in this statement you can replace positive definite by negative definite if you replace local minimum by local maximum. Very often we will consider unconstrained problems so that S simply becomes Rn in this statement. This statement is consistent with what we know for functions with one variable. Let us take an example, a very simple one, where we have a function of one variable. F of x is equal to x squared, and well, the function looks like this, right? And you know that the minimum is in 0. So indeed, if we take x star is equal to 0, we see that, well, the derivative of f of x, 2x in 0 is equal to 0, and we have that the second derivative in 0 is simply 2. We have a positive curvature, an upward concavity, so we have here in x is equal to 0 a minimum. Note that these conditions are sufficient conditions. They are not necessary and sufficient conditions, which means that you can have situations where these conditions are not met and you still have a local minimum. To illustrate this, use simply the function f of x is equal to x to the power 4, and you have a very similar plot than with the function f is equal to x squared, except that things are going to increase much faster when x is increasing. So we know that we have here a local minimum in 0, so again we'll consider x star is equal to 0, and now we have f prime evaluated in 0 is 0, so this condition here is met, and we have that the second derivative evaluated in x star is also 0, so this condition is not met, but still we have a local minimizer here, x star is equal to 0. So this shows that these conditions are sufficient but not necessary. It is quite easy to see where those second order sufficient conditions are coming from. What we have to do is to write the Taylor series expansion of f of x in the neighborhood of x star. So let's do this. We'll consider f evaluated in x star plus dx, where dx is a small perturbation, and now we write the Taylor series expansion. F of x here is a scalar valued function, but the input is a vector, right? So what we'll obtain is f of x star plus the first order terms. They involve the gradient of f evaluated in x star transpose times dx, right? So this will also be a scalar, a row vector times a column vector, plus a half dx transpose, then the Hessian of f evaluated in x star times dx. So this again will be a scalar, and then we have to take into account the higher order derivatives that we neglect, right? If dx is small, this will give you only a very small contribution, right? Well, from this statement we see that this term is 0, and this matrix over here, the Hessian evaluated in x star, is positive definite, so this will be a positive term, right? So if dx is small enough, what we'll have is that f of x star is smaller than f of x star plus dx. So indeed x star is a strict relative local minimum. In order to use this result, what we'll do is look for critical points. A critical point is a point x star that meets this condition, right? So it's a list of all x stars such that, well, the gradient of f in x star is equal to 0. When we have identified the critical points, because usually there are several critical points, we have to look for the Hessian and evaluate it at the critical points. If the Hessian is positive definite, then we have a local minimum. If the Hessian is negative definite, then we have a local maximum. If the Hessian is indefinite, so neither positive definite nor negative definite, then we have a saddle point. Let us take a very simple example of a scalar valued function with x in R2. So there are two variables, x1 and x2. We can compute the partial derivatives. First, partial derivative with respect to x1, so that's 2x1. The partial derivative of f with respect to x2, that's 2x2. And then we can take second order partial derivative, so with respect to x1, so that yields a 2. This will also be the partial derivative of x, second partial derivative with respect to x2, right? And if you take the second order partial derivative first with respect to x1 and then with respect to x2, that's 0, right? So if you take this one and you take the derivative with respect to x2, this yields a 0. And this is how we obtain the gradient, and this is how we obtain the Hessian, right? And we can now look for critical points. These are the points that make the gradient 0, and you can see that there is only one point, and that it corresponds to x1 is equal to 0 and x2 is equal to 0. So that's the origin. So to see if this critical point is a minimum, maximum, or saddle point, what we have to do is to evaluate the Hessian at the origin. But as you can see, the Hessian is independent of x1 and x2, so the Hessian, whatever the point, is always this matrix, and it's obvious here. And these are the diagonal elements, the pivots, they are both positive. Well, it's clear that this Hessian is positive definite, right? So the origin is a local minimum of the function f of x, as we had kind of expected. And indeed, this is a graphical representation of the function, and as you had expected, it is a paraboloid with a minimum at the origin. Well, we can do another exercise with a function that is very similar, except that we have a minus sign over here. If we compute the gradient, this will produce a minus sign over here, and if we compute the Hessian, it will produce a minus sign over here. But the origin is still a critical point. So what we have to do is to evaluate the Hessian at the origin, and again this Hessian is independent of x1 and x2, and it is neither positive definite nor is it negative definite. So the origin is not an extremum. Extremum is not a word for minimum or maximum. In fact, it is a saddle point. This is the graphical representation of the function x1 square minus x2 square, and you can see that at the origin we do not have a maximum or a minimum. You can clearly see where the name saddle point is coming from, because we have the shape of a saddle here. You can see here that in the x1 direction we have an upward curvature, and in this x1 direction, well, we have a minimum, whereas in the cross direction, in the x2 direction, we have a downward curvature, and in this direction a maximum at the origin. Well, let us do an exercise. So the question here is to find the critical points of the following function and to decide whether they are minima, maxima, or saddle points. So push the pause button and try to do the exercise by yourself. So here's the solution. So of course the first thing that you have to do is to compute the gradient, and that's a column vector, and then you have to compute the Hessian, and since there are two variables, this is a 2 by 2 matrix. Since there are no cross terms over here, so terms that involve x times y, well, this Hessian is diagonal. To find the critical points, we have to find for solution points that make the partial derivative of the cos function with respect to x 0 and at the same time make the partial derivative of f with respect to y 0. But since here this equation only depends on x and this one on y, we can treat things separately. Here we have two solutions, plus minus 1. Here we have three solutions, plus minus 1 and 0, and this yields, well, 6 critical points because we can combine, right, the plus minus 1 for x with the three solutions of this equation, 0 and plus minus 1. So at the critical points, right, we can have a look at the Hessian, and for instance for this critical point 1 0, the Hessian is clearly negative definite, and here we have a maximum. For the three next critical points, we can clearly see that the Hessian is indefinite, so we have in each of these cases a saddle point. And for the two last critical points, we can clearly see that the Hessian is positive definite, so we have a minimum. Well, let's do another exercise. So find the extrema or saddle points of this function. Again, try to do this exercise by yourself first. Let us have a look at the solution. So the first thing that we have to do is to compute the gradient and the Hessian. I assume that you can do this and that you can work with partial derivatives. Then we have to look for the critical points, and the critical points make the gradient 0. Okay, so we have to solve this system with two equations and two unknowns. Well, there are two alternatives. Well, alternative 1 is, well, setting this one to 0, right? Then you have fixed x, and to put the other one to 0, well, you set the sine of y to 0. You can work also with the second alternative, in which you make cosine y 0. If y is then fixed, well, then you have to fix sine x to 0 to make sure that the second equation is 0. So here are the solutions. X, well, that's pi over 2 plus k pi, and y is k pi, where k is some integer, right? And we can similarly find the solutions for x and y for this second alternative. So what we'll do is work in the interval 0 to pi, and 2 pi is not taken into account. Of course, you can find all the other solutions, right? Because you know that this function is periodic. So in this interval, if we consider alternative 1, you can see that there are 4 critical points: pi over 2 0, pi over 2 pi, 3 pi over 2 0, and 3 pi over 2 pi. You can see here that because cosine x is equal to 0, that the off-diagonal terms will be 0 in the 4 alternatives, and then you have to plug in the values of x and y and compute the Hessian. And you can see that there are two cases where the Hessian is negative definite, and this leads to maxima in pi over 2 0 and 3 pi over 2 pi, and there are two cases where the Hessian is positive definite, and in these cases, well, you have minima in pi over 2 pi and 3 pi over 2 0. We can now consider the second alternative, and in this alternative, because we make the sine of x 0, we have that the diagonal terms are 0, as you can see. And because we have had a course on linear algebra and that we know that the trace is 0, we know that the sum of the eigenvalues must be 0. So we have two eigenvalues of opposite sign, and therefore this matrix cannot be negative definite, nor can it be positive definite, so it must be indefinite, and these 4 critical points therefore correspond to saddle points. If you have access to MATLAB, what you can do is verify the result that you have obtained by using a surface plot and this MATLAB code over here. So let's do this. So this is the surface plot you obtain, and what you can do is have a look, and you can see, and this is then alternative 2, that when x is equal to 0, well, there is no value of y that gives you a minimum or maximum, and this is also the case for x is equal to pi. Okay, so this corresponds with the facts that those 4 critical points were yielding a saddle point. When x is equal to pi over 2, we see that we have a maximum when y is equal to 0 and a minimum when y is equal to pi. And when x is equal to 3 pi over 2, we have a minimum when y is equal to 0 and a maximum when y is equal to pi, and this corresponds to the results that we had obtained for alternative 1. Convex functions play an important role in optimization. A convex function can be seen as a kind nonlinearity. Convex optimization problems are problems where the objective and constraint functions are convex. Such problems are easier to solve, and in general, reliable algorithms are available to find the underlying solution. Well, let us start by looking at what we call a convex combination of two vectors, x1 and x2, that will be living in general in Rn, and a convex combination is a combination alpha 1 x1 plus alpha 2 x2, where the sum alpha 1 plus alpha 2 is equal to 1, and alpha 1 is positive and alpha 2 is positive. This definition of a convex combination can be extended to several vectors, so more than 2 vectors. If you have 2 vectors, such as what we have in this case over here, we can rewrite this and make the notation a little bit easier and write it as alpha x1 plus 1 minus alpha x2, where alpha is a real number that lies in the interval 0 to 1, right? And as you can see, every convex combination of 2 points lies on the segment between the 2 points. We can now have a look at the definition of a convex function. The general definition that you see here below is for a function with input x that is in Rn and produces an output that is a scalar, but the representation that you see here above is for a function of one variable. A function is convex if for any two input vectors x1 and x2 the image of any convex combination of x1 and x2 is smaller or equal than the corresponding convex combination of the images. Let us have a look at this example of a function with one variable, and let us take any x1 and x2 and take a convex combination of x1 and x2. So this will produce a point that is lying on the segment that joins x1 and x2. Let us say this x over here. Well, the image of this x, and here's its image, must be smaller or equal to, well, the same convex combination, but now acting on the images of x1 and x2, right? So this convex combination will be somewhere over here, and it will produce an image that is over here. So for the function to be convex, the image of any convex combination of x1 and x2 must be smaller or equal than the corresponding convex combination of the images. So in practice, this means that any segment joining 2 points on the graph of the function f of x must lie above the graph of f of x, and this is clearly the case with this function. So this function is a convex function. If there exists segments connecting 2 points of the graph of f of x that partially lie below the graph of f of x, then the function is said to be non-convex, and this is clearly the case with this example. Note that this function is non-convex if we consider a domain for x that is R, the set of all real numbers. If we restrict the domain to the interval x3, x4, right? So if the domain of f is the interval x3, x4, then we can see that this function is indeed convex on this restricted domain that is the interval x3, x4. A few additional comments can be made. Notice that for a convex function, well, we have a function that bends upward. We speak of a positive curvature. Here we have defined a convex function, but we also speak of strictly convex functions, and then you have to replace smaller or equal by smaller. Of course, you can also speak of concave functions, and then you have to replace smaller or equal by greater or equal. For concave functions, the curvature is negative. Likewise, we can speak of convex feasible sets. If the feasible set is convex, it means that all connecting lines between any feasible points are in the feasible set. And so this is an example of a convex feasible set. In this example over here, you can see that, well, some connecting lines between two feasible points, right, are not entirely in the feasible set. So this is a non-convex feasible set. An optimization problem is convex if the objective function is convex and if the feasible set is convex as well. It's possible to show that for convex problems, the unique local minimum is also a global minimum. As said before, such problems are easier to solve, and in general, reliable algorithms are available to find the underlying solution. Note that a maximization problem on a function f of x that is concave, and where x is constrained to live in a feasible set S that is convex, is also considered as a convex problem, because you can rewrite this optimization problem as minus the minimum over the objective function minus f of x, where x is constrained in the same feasible set S that is convex. If f of x is concave, well, minus f of x will be convex, right? So this problem is convex, and therefore this one is also considered to be a convex optimization problem. To check that a function is convex on a domain, you have to compute the Hessian and check that it is positive semi-definite for every x in the domain. Remember that the matrix A is positive semi-definite if x transpose AX is larger or equal to 0 for every non-zero x, right? Well, let us take the Hessian of our paraboloid. F of x is x1 squared plus x2 squared. We had seen that the Hessian was a diagonal matrix with 2's on the diagonal. Here we have clearly a positive definite Hessian, so the function is strictly convex, and the local minimum that we had found at the origin is clearly therefore the global minimum. Let us consider a function that is slightly more complicated, a function of three variables, x1, x2 and x3. The gradient will therefore be a column vector with three elements. This is the partial derivative with respect to x1, partial derivative with respect to x2, and this is the partial derivative with respect to x3. The Hessian will be a 3 by 3 matrix. So for example, this is the second derivative with respect to x1. This is the second derivative, first with respect to x1 and then x2, and so on. Well, we have to check that this function is positive semi-definite, but here in this case, the upper left determinants, also called the leading principal minus, so the determinant of this matrix, this determinant over here, which is a scalar, and this determinant, well, you can check that they are all positive, right? So this Hessian is actually positive definite for all x in R cube. So this means that this function is strictly convex. So we see here that the origin that makes the gradient 0 is a local minimum, but it's also the global minimum. It's kind of obvious from this function over here because we have a sum of squares and one term which is the fourth power, right? So this is always larger or equal to 0. So if the origin is a local minimum, we see here that it's also the global minimum. Let us do an exercise. The idea here is to prove that this function is strictly convex on R cube. Please push the pause button and try to do the exercise by yourself. First we compute the gradient of the function. So it's a column vector with 3 elements. The Hessian will be a 3 by 3 matrix, and here we can check if it is positive semi-definite or positive definite. So for instance, we could compute the upper left determinants, also called the leading principal minus, and you can see here that they are all 3 positive. Here the determinant is constructed on the last line to make things easy. So you can see clearly that the 3 determinants are positive, so this matrix is positive definite. What you can do is compute the pivots, and for that you have to use elimination. This is the pivot, and the multiplier is easily computed. It's the element to eliminate divided by the pivot, and this is what you obtain after elimination. And you can see clearly that the 3 pivots are positive. And to check, if you multiply here the pivots, because this matrix is in upper triangular form, you can see that you obtain the determinant, which is consistent with what you have over here. So this Hessian is positive definite over R cubed, so the function is strictly convex, and we can see here that the local minimum, which is the origin, right? You can see that the gradient is 0 at the origin. Well, therefore the origin is also the global minimum. Here's another exercise. You have to test the convexity of this function. So here's the solution. Well, first of all, you have to compute the gradient. Okay, so this is the partial derivative with respect to x. If you take the derivative of this one with respect to x, well, it's the exponential itself, right, times the derivative of x plus y, and that's 1. So this explains this term. The partial derivative of the exponential is the exponential itself, and then here the partial derivative of minus x, and you have minus 1. I'll leave you the partial derivative with respect to y, and this is what you obtain. And you can notice that when x tends to minus infinity and at the same time y tends to infinity, well, this gradient will be 0. Okay, this term over here will tend to 1, this one as well, and this one will tend to 0, right? So we have a minimum when x tends to minus infinity and y tends to infinity, and this minimum is 1. You take the function and you take this limit, and this is what you will find. The question was about convexity, so we have to compute the Hessian. Here it is, right? And then we compute the upper left determinants, or the leading principal minus. Well, obviously this determinant here 1 by 1 is positive or 0. It can be 0 when x tends to minus infinity and y tends to minus infinity as well. Then if we compute the determinant of the Hessian, this is what we obtain, and again here we have something that is positive or 0. So this function is convex on R square, and this minimum that we have found is the absolute minimum. Let us have a look at a surface plot of this function. Here we'll look at the general surface plot, and then we'll zoom at what happens for small values of z. So this is the overall surface plot, and you can have a look. And of course, when x is taking large values and y is taking large values, you have here of course z taking large values. In this second plot, it's the same function, but we zoom at what happens when z is small, and then indeed you see then when x is tending to minus infinity and that y is tending to plus infinity, we have here something that tends to a minimum, and this minimum is indeed 1, as you can see. Well, since this is so much fun, we'll do another one. Here we have a function that depends on the parameter a, and the question is for which values of a is the function convex, and again try to do this by yourself. Here is the solution. So as usual, first we compute the gradient and then the Hessian, and by now you should be able to do this. And in this case it's easier to use the method with the upper left determinants, or the leading principle minus. This one over here is a scalar determinant, obviously it's 4. This determinant over here is 0, and then you have the determinant of the Hessian, and here the determinant is constructed using this line over here, and you see that you have minus 16a square. You have a 4 and a 0 over here, so the only thing that you can have is that you could have a Hessian that is positive semi-definite when a is equal to 0. So when a is equal to 0, the Hessian is positive semi-definite, so the function is convex, but not strictly convex. When a is different from 0, well, the Hessian is indefinite and the function is therefore not convex. Optimization problems can be distinguished by a number of characteristics. The complexity, of course, depends on the number of variables and also the number of constraints. In most optimization problems, and in all the problems that we'll consider in this course, the variables are continuous in nature. But sometimes variables are discrete in nature and, for example, only take integer values. We will see an example later, but as I said, this goes beyond the scope of this course. The difficulty of the optimization problem depends on the properties of the objective function. So the number of local minima, is the function linear or nonlinear? If the function is nonlinear, is it quadratic, convex? And of course it also depends on the smoothness of the objective function. This means, is it continuous? Is it differentiable? The optimization complexity, of course, also depends on the presence of constraints, equality or inequality constraints, the type of functions that are involved, linear or nonlinear, and if nonlinear, convex or not. And again, of course, smoothness, that is, continuity and differentiability, plays an important role. The first class of optimization problems that we'll consider, and we'll consider them in the next section, section 3, is the linear program. The objective function is linear and the constraints are linear as well. So we have a linear optimization problem. Note that it does not make sense to consider a minimization or maximization problem with a linear objective without constraints. Let us take an example of a linear objective function of one variable, for instance ax plus b. We can very easily obtain the graph of this function. So here we'll have 0 b, right, and here you'll have minus b over a, 0, and this is the graph of the function. And you can see that if there is not a constraint here, well, the problem is trivial. Maximization will lead to x tending to infinity, and a minimization will tend to, well, x tending to minus infinity. It only makes sense to treat problems where you have constraints. So for instance, x smaller or equal to x max, and for instance x larger or equal to x min, right? And in such a problem, if you have a maximization problem, the maximizer will lie over here, and if you have a minimization problem, well, the minimizer will lie over here. In this very simple linear program, you can see that the solution is always an extreme point or a vertex of the feasible region, and this will generalize to more complicated linear programs. We'll see in the next section that many practical problems in operational research can be expressed as linear programs, and each time the linear program can be rewritten in this standard form, right? And this is the case even if you have a maximization problem, or even when you have, well, inequality constraints. And in this standard form, you recognize here the linear objective function. You have linear equalities under the form ax is equal to b, and the variables are constrained to be positive or 0. If you look at the constraints, well, this leads to a feasible region that is a convex polytope. Don't worry, this is a very complicated word, but for n is equal to 2, the polytope is simply a polygon. This is something that you know. And for n is equal to 3, a polytope is a polyhedron. So a polytope is simply a generalization for a general n of a polygon or a polyhedron. In this course, we'll present and use the simplex method. This method dates back from 1947. There is also a more recent method called the interior point method, but this method goes beyond the scope of this 15-hour course. For your information only, you might wonder what is a simplex and why the method is called the simplex method. Well, a simplex is a generalization of the notion of a triangle to arbitrary dimensions, so to a general n. Simplices are not used in the simplex method, but they can be used to give an interpretation of the method, and this is where the name simplex method comes from. The next class of optimization problems is the integer programming problem, and this is for your information only. In this case, the objective function is linear, and so are the constraints. Well, some or all of the variables are integer, right? So when all of the variables are integer, this problem becomes the following one. This is very similar to what we had in the linear program, but here x is constrained to be positive and to be an integer. One example of such a problem is the famous traveling salesman problem to determine the fastest or shortest round trip through n locations. Let us have a look at this traveling salesman problem, problème du voyageur de commerce, in Wikipedia. So we have a number of cities, we have n cities, and the distance going from city I to city J is Cij, and of course this distance is positive. We are doing the optimization on the variables xij, and xij is really the question: is the path going from city I and city J included in the travel, yes or no? So xij's are binary values. So this is how we write the optimization problem. So we minimize the distance, of course with a number of constraints. The xij are binary values. We have to make sure that you arrive at a city only one time, and you have to depart from the city only one time and not more than one time. This is a more technical constraint, and it makes sure that you end up with a solution that is a single tour and not the union of several smaller tours. For your information, quadratic programming problems are programming problems where the objective function is quadratic and the constraints are linear. You have equality constraints and inequality constraints. If the matrix Q in the objective function is positive definite, then you have a convex optimization problem. These type of problems play an important role in general nonlinear programming problems, because when you are near to the local minimum, well, then the objective function is almost quadratic. For your information, nonlinear programming problems are problems where in general the objective function is nonlinear and the constraints are nonlinear, and you have equality constraints and inequality constraints. In general, the problem is non-convex, but we have seen that if all of the involved functions are convex, then we have a convex problem. And the difficulty here, is also related to the smoothness of the underlying functions. Are the functions f, g, and h smooth? So are they continuous? Are they differentiable? In section 5, we'll look at a subclass of problems where there are only equality constraints. And this will lead to the Lagrange multiplier method, where we have a general non-linear objective function and one or several equality constraints. In the course of state space control methods in the teaching unit Advanced Control 1, we have looked at optimal control. This type of problem can be written in the general nonlinear case, where a cost function is minimized given a state space description of the process, and this state space description acts as a constraint. In the course of state space control, we had considered optimal control for linear descriptions of the system, and this had led to LQR design, where Q and R are the names of the functions that appear in the cost function that is to be minimized. For one particular case of Q and R, so Q is C transpose C and R is lambda times an identity matrix, well, the problem reduces to this one, and you can see that here you have a trade-off between minimizing the output energy and minimizing the control energy, and you can use this variable lambda to kind of play with this trade-off. In the course of state space control, we have introduced this LQR design for both continuous time systems, this is the case over here, but also for discrete time systems, but we only have used an infinite horizon because it leads to a controller, an LQR controller, that is time invariant. In the course of my colleague Thomas Museur, Model Predictive Control, you'll work with descriptions that are discrete time, so the integral will become a sum, and you'll also work with horizons that are no longer infinite, so this will lead to a controller that is time variant and will lead to the concept of a receding horizon. Another difference when you compare model predictive control with LQR design is that you can add constraints, equality constraints and inequality constraints. If you have a model predictive control problem with equality constraints only, then you can use the Lagrange multiplier method introduced in section 5 of this course to obtain an analytic solution. If there are inequality constraints, then an analytical solution is no longer possible. Of course, there is a last class of important problems, and it's the class of least squares optimization problems, and that type of problem we have encountered in the course Linear Algebra and Applications. Well, those type of problems can always be rewritten with an objective function of the type that is shown here on the screen, and we had seen that there is an analytical solution that is given over here. If necessary, you can review this topic as the course is available online. One application of this type of optimization problem is the estimation of ARX models using a one step ahead prediction in the course of linear system identification.